In the previous video on circular functions, we saw that sine and cosine were not just something to do with angles, but were actually functions in their own right. You can put any real number in and you get a real number out. These functions are useful when it comes to angles and triangles for sure, like you've seen in earlier work in maths, but they are much more than just angles and triangles. In this video we're going to look at their graphs, just as we did with other functions such as exponentials, quadratics and so on. On your screen you can see the usual vertical and horizontal axes. The horizontal axis is the real number line, or in terms of the earlier video, the length of the red piece of string. Now I've chosen to put the scale here in terms of pi instead of the usual 1, 2, 3. Doesn't alter the shape of the graph at all, but it's just easier to see where special things happen, where crossing of the axes and so on is often at multiples of pi, and it's just easier to do it this way. But don't be put off, it's just the ordinary number line. And here we'll give it the same name as we did in the other video. We'll call that axis the t-axis. And the vertical axis is the value of the function we're looking at each value of t. So it could be sine of t or cosine of t. Let's start with the cosine function. So for t equals 0, cos of 0, the x-coordinate, was 1. And the y-coordinate, sine of 0, was 0. Then if we made our piece of string pi by 2 long, so cos of pi by 2 is 0, sine of pi by 2 is 1. Let's do this now for all the different t's from 0 to 4 pi, just to get a feel for what's happening with cosine. So there we go. As t gets bigger and bigger, cos of t takes different values because p is going around the circle, remember? And at 2 pi, it starts to do it all over again because the period of this thing is 2 pi. Okay, now in the last video, at the end of it, I briefly mentioned that t did not have to be positive, even though that's all we've been looking at up till now. In terms of the picture with the piece of string, the string could get longer and longer going down the screen, not just up it. So if the string is going down, we can call that negative, and we then wrap this clockwise around the unit circle, whereas before, when t was positive, we wrapped anti-clockwise. But now we're going negative, so this is our negative length of string going down, and there we go. That's our cosine function. So we've got a pretty good idea of what this thing looks like, and in fact here it is complete. That's the cosine function going on and on forever, both ways. And we can do the same for sine of t. So we'll start at 0 because that's where we're most familiar with from the other video. T at 0 going up to, we'll stop at 4 pi just to get an idea, and here we go. So it behaves a little bit like cosine but different. It's still periodic, it's going up and down as t gets bigger, and the same thing with negative t. Back I go. T is, and here we go, just has the same behavior whether t is positive or negative. Both sine and cosine have obvious strong symmetry properties. Let's look at sine while we've got it here. It's not quite a reflection about either axis, is it? It's not reflecting about the y and it's not reflecting about the x. But if you do a double reflection about one axis and then about the other, you've got the function back. So we give this a special name. Any function like this, where you reflect it about one axis, then about the other, we call that an odd function. Another way of putting that is that every point is symmetric through the origin. So let me see if I can show this. This point, if I go through the origin and then keep going the same distance, I'll end up at this point there. This one go through the origin, keep going the same distance, I'll end up with this one here. So there is this point symmetry through the origin or the double reflection. They are equivalent. So here we have an odd function. And if you like the algebra for it, it's f of t equals negative, that's reflecting it in the y-axis, negative f of negative t. And that second negative there is reflecting it in the x-axis. Okay, what about cosine? That's actually a lot easier, isn't it? That's just a direct reflection in the y-axis. And so we call that an even function, where f of t equals f of negative t. So f of t equals f of negative t. Wherever t is, it's balanced. F of t, same as f of negative t. That's an even function. So you need to know these terms, even and odd functions. Now we come to the third circular function, which we haven't really talked about much yet, the tangent, or for short, tan of t. It's defined as tan t equals sine t divided by cos t. So if we know sine and cosine, we can quickly find the value of tan for any value of t. Well, we want to know what this looks like as a graphed function, of course. From your earlier work on functions, you know that as soon as you have a division, you have to get a little bit nervous. Why? Because if the denominator is ever 0, the function does not exist there. It's not defined. We're not allowed to divide by 0. Well, is that going to happen with tan? Remember the denominator? Tan t equals sine t over cosine t. Is cos t ever 0? Well, is it ever? Let's have a look at it. Here, and here, and here, and here. Oh dear, and here. It's 0 in many, many places. Ouch. In fact, it's 0 at every odd multiple of pi by 2. Well, there's nothing we can do about it. We just have to accept it. So sine and cosine then are defined for all real numbers, but tan has many points where it's undefined. Let's graph it now and see what it looks like. So yes, that's what we're expecting, isn't it? It's going off to infinity at many points and negative infinity at many other points. And there is a symmetry about it, which is nice. Now, these points where it's undefined, remember we have a special name for them from our other function work. It's just the same here. We call them asymptotes, don't we? So we can draw lots of asymptotes on the tan graph. And just to help us see how it's behaving, let me put those in now. So now you know the shape of all three main circular functions, cosine, sine and tan. You know properties of symmetry about even and odd. And by the way, you need to be able to say whether tan is even or odd. And you know now that tan has many asymptotes, many places it is not defined, whereas the sine and cosine are defined for all real numbers. Let's go back to the cos graph now and learn a bit more about it as a function. Now I've been calling it a function all along, but how do we know it is from the graph? Of course, it passes the vertical line test. That's how we know. There is no value of t that has more than one value of cos t. Good. What about its inverse though? Will that be a function? No, certainly not. Look, you can draw many horizontal lines that cut the graph in many places. Ouch, that's not so nice because it's often handy to have the inverse. We like to use it in algebra. But remember, we have a nice trick we learned in our other function work when we have this problem. We can restrict the domain of the function so that it now passes the horizontal line test and its inverse is a function too. In other words, if we want cos t to have an inverse, we can no longer define it with all the real numbers as the domain. We have to find a small part of the real numbers where there are no repeats, where the horizontal line test works. For example, that could be from t equals minus pi to 0, or from t equals 0 to pi. I mean, there are many, there's actually an infinite number of these areas where the horizontal line test would be passed. But you do have to restrict the domain in some way like this, just to a very small section. There's a lot of them, but they're quite small. And again, we have to be careful to make the restriction of the domain so that the horizontal line test will work in the restricted part of the function we're looking at. And here you'll have a different set of, a different interval of t to achieve that from with cos t, but it's the same basic principle. Once we've restricted the domain, what does the inverse actually look like? Okay, so here's cosine of t back again, and now we will restrict it to the domain where it passes the horizontal line test. So now this function, with the very restricted domain, this function will have an inverse that is also a function. What will it look like? That. So that's our inverse, and we give it the name arccos. So the red function is y equals cos t. The black line there, that function, is y equals arccos t. Now, knowing what you do about the cosine function, the red one, and about inverses, you can tell me straight away what this point will be. It's the one that's been reflected about the y equals x line. And where did it come from? It's the inverse of this extreme point here, isn't it? And we know that point. Its x value was pi, and its y value was -1. So the inverse, what do? We swap the coordinates, don't we? Up we go. So this will be -1 pi. And finally, what about the inverse of sine t? Well, here's our sine function. We have to restrict the domain, so let's go ahead here. We've done that. We put in our mirror line, and we do the reflection. There. So there's our inverse functions. They're the trickiest bit. If you're going to be doing inverse circular functions, you've got to remember to restrict the domain of the circular function itself.